Many of the reactants that we will see in our chemical equations will need to be dissolved in water before they are mixed. This is because reactants like ionic compounds don't have great mobility if their ions are locked in place. Allowing those ions to travel around a solution increases the chances of them finding other ions to interact with, which in turn increases the likelihood that new products could be formed. As such, many reactions are run with compounds in solution, meaning whatever you're trying to react has been dissolved in some bulk liquid referred to as a solvent. In Gen Chem, we pretty much limit our solvent to water, which is more than fine because water is an amazingly versatile solvent that can do a lot of good work for us. The reactions in section 2.2 and 2.3 are all going to involve aqueous solutions, so it's probably a good idea to get a handle on what it means to be dissolved in water and to form an aqueous solution. This subsection will seek to do just that. You are undoubtedly familiar with H2O, probably in all of its states of matter, each of which has its own unique common name, by the way. Water does not describe all three states of matter. The structure of the H2O molecule gives rise to H2O being an exceptionally useful and versatile compound. You probably noticed that the molecule has a bent shape, looks kind of like a V. This shape means that the hydrogen atoms, the white ones, which have very little electron density around them, are sequestered to one side of the molecule, while the oxygen atom, the red one, which has quite a bit of electron density around it, is sequestered on the other side. Think of that electron density in terms of what water might like to interact with. If something has less electron density, such as the hydrogen atoms, then that thing will have some positive character to it. Opposites attract, so that positive character will seek out something with negative character to partner up with. Opposite story is going to be true for the oxygen. Since it has lots of electron density around it, it ends up with negative character and seeks out positively charged things. That character is better referred to as partial charge here because I'm describing an uneven distribution within a molecule. So in grown-up terms, we can say that the hydrogen atoms have a partial positive charge and that the oxygen atoms have a partial negative charge. The chemist uses a lowercase delta to denote this partial charge. The difference in partial charge from one side of the molecule to the other makes water a polar molecule. The dual nature of this molecule created by that polarity means that water is pretty darn good at dissolving things that have a similar nature as itself. It's a great and widely used solvent and is sometimes, although kind of inaccurately, referred to as the universal solvent. That takes it a few steps too far, as water does in fact not dissolve everything, as anyone who has added sugar to cold tea is aware. It's a really good solvent for many varied samples though, and is a solvent we choose to focus on in general chemistry. Now, we need to discuss adding something to our super amazing solvent. The chemist will describe substances as soluble or insoluble. To be most accurate, we should add that a substance is soluble or insoluble in whatever solvent we're talking about. For instance, we should say sodium chloride is soluble in water. But that last point is usually lost on Gen Chem because water is our go-to. So to be soluble in this section and really this course, it has to be easy enough for your compound to play along with the ideas presented in the following animation. If it's too hard for the water molecules to surround the areas of different charge, then it's unlikely you'll make a solution. Or if there isn't a big enough distribution in charge initially, the following can't occur. Now let's see if we can illustrate why water is so great. We'll start with a molecule of hydrogen fluoride. Much like water, hydrogen fluoride has an area with less electron density and an area with more electron density. Or, in other words, hydrogen fluoride contains areas of opposite partial charge. Since the two molecules tell similar stories, it's reasonable to expect hydrogen fluoride to be soluble in water and form a solution. This is because when molecules such as HF are placed in a solvent like water, the individual water molecules begin to move towards the addition and align themselves with the different ends of the polar molecule. Notice that the oxygen atom, or the negatively charged ends of the water, align with hydrogen from the hydrogen fluoride, and that the hydrogen atoms, or the positively charged end of the water, align with the fluorine from the hydrogen fluoride. Once everything is nice and aligned, the water molecules carry off the now solvated ions so that they can go do chemistry. Some notes. There's a difference between these partial charges that we have given the molecule and the total charges that these ions carry. When potassium bromide forms, for example, The electron from potassium is transferred to the bromine to form bromide. It's not associated with potassium anymore, so we wouldn't use these delta symbols in that case. We would only use them with molecules. Even so, I had put a salt into water, the water molecules would surround the ions in a similar way as it surrounded these then atoms but now ions in hydrogen fluoride. Then the oppositely charged ions separate from each other and spread throughout the solution. Second point, animations in PowerPoint are hard, so there were limitations to what I could do water molecule wise. There would be many more molecules per ion than what I can show here, and they would arrange themselves in 3 dimensions around each ion versus in the plane like I can show here. Think balls versus circles. Might seem like a light point, but it's actually pretty important because if there are water molecules on all sides of the ion, that ion doesn't have to do much thinking about how to interact with the solvent anymore. The solvent will do that for it. This makes these ions highly mobile when solvated, which gives them a much better chance of reacting. Your solvated ions won't use up all of the water molecules in your sample, so there will always be leftover water molecules, kind of like I show here. You're going to end up with however many spheres of hydration, that's the ion with the water molecules around it, as there were ions in the ionic compound or ions that could be formed from your molecule. The hydrogen fluoride molecule we saw would dissociate into 2 total ions, each of which would form a sphere of hydration. This is denoted by the AQ on the product side. Similar story for a formula unit of potassium bromide or a formula unit of barium sulfide, at least before it further hydrolyzes. Calcium chloride, though, contains 3 total ions and thus would produce 3 hydrated ions when added to water. Iron 3 sulfate would produce 5 ions when added to water. You'll see more regarding dissociation equations such as these in the next section, and more detail is provided there. But for now, I encourage you to pause the video and compare and contrast what is given on the reactant side with what is given on the product side. Note how the states of matter change from one side to the other. Note how the charges are included on one side but not the other. And probably most importantly, write yourself a rule to explain the relationship between the subscript on the reactant side and the coefficient on the product side for any of the ions.